Okay, so this is a Champlain Towers South. There's a webinar with 4 professors in it, engineers. You guys may have difficulty listening to this. This is a shout out to my girl Tears there. She's learning doing some Spanish at nighttime, and I said I'd give her a rumble reply, but let me jump into that reply right here for her. Okay, so you can hear me speak, and it sounds like English to you, and you can probably determine which English it's from. Is it United States or North, South, whatever. And that's because sometimes Southern English might have a little bit of draw on it, as you guys would know. A little draw, a little lag, right? A little, how y'all doing? A little drag to it. It's still the same words. They are still the same words. All right. Now here's the thing. We have this little guy right here. This little right there. Let's hear it.
Larynx.
And it states it's a hollow muscular organ forming an air passage to the lungs and holding the vocal cords in humans and other mammals, other voice box. Other animals, birds, dogs, cats, they all have their own little vocal cords. All right. So let's just get you an image of vocal cords and let's go from there. This will tie in to help you understand, to help you translate the harder English, if you will. So it's going to tie into the video, so bear with me. So here's our vocal cords. And while I'm speaking, I'm letting air blow out and I'm getting words out, Hello, what time it is? Can you tell me what time it is? All in one sentence. So it kind of fades off in there because I can't make these vibrate as much as when I initially started saying the words, starting a sentence. So each word as a child, I learned how to say hello. And I know how to make this vibrate with air now. And that's all you're doing. You're sending air up to teach these vocal cords to vibrate and put a frequency out that says the word hello. And someone else learning a different language, they'll have to learn that frequency also, the word hello. So if you're trying to learn the word hello and you speak Spanish, you might say hello differently because you're not used to being pounded by other people next to you practicing the word hello to get that frequency. And so the hello sounds a little bit hello. You're like, oh, no, hello. Like a W on the end of it, right? And so you're trying to tell them that, and they're like, well, I don't get how to add the W on it. Just how it sounds to you. So that's a pretty difficult thing to do. So Tears is learning Spanish as she's doing, and I've got a lawyer friend of mine. He's learning right now Russian and also Japanese. So he has to teach his vocal cords how to sing along those words, how to make those words, these vocal cords vibrate with the air in his lungs. So we have the same air, but we have to learn how to make those vocal cords vibrate to sound like that foreign language that we're trying to speak. And it takes, multiple cycles before you can say, I know how to say the word. Like some of you say niet or Nastravia, hola. Things like that you taught yourself how to say. Those aren't English words, but you taught yourself how to say certain things. Como está? So I say it slowly because I don't know how to. I have to say it slowly, mindfully. And I don't even know if I said that correctly, but the vocal cords there, they vibrated. I had them vibrate in that other language. And so as you're learning as you're listening, forget that. Now let's go back to the video content. So if you come here and you listen to the people here, they're from India, and you're going to hear them speaking English. And some of you say, oh, it's so hard to understand them. Well, remember, they have maybe not their native language, and secondary language, rather, what I mean. And you have to teach your brain, your eardrums, to pick up the frequency, to change the beat, to say, okay, to catch on. For example, I'm a very fast talker, and I have to force myself to talk slow in my videos with you that I'm communicating with you now. Otherwise, my brain and my language goes very fast, sort of like my writing. It'll tail off. Hell, even me, when I'm finished my notes, I look at them like, what the hell is that? Even I need a decoder for my notes. So I know that I can speak too fast. All right. So if you come here and listen to it, it's 2.5 hours long. 2.5 hours, 2.3 hours, yeah, 2.3 hours long. I'm there. So now they're into, so if you do this, I'll give you the short version. They're really into punching shear. It's about the size of it. It's 4 months. Yes, they do a nice presentation. They really want to get into stiffness in the pad. They want to talk about the rebar that was not in across the columns. They do show the rebars across 2 columns at top, but not the lower steel. I've put my comment down here to tell them, look, reach out to me. I'll tell you wherever you want to go on this building. There is steel in the lower part of the slab there that goes through the column at the parking garage area. Just because you don't see it doesn't mean it's not there. Remember how rebar pops and how it pulls away. The other thing is I show you what I call the roach antennas, and a lot of people, including these people, another engineering group that I watched the other day, they think the rebar is like going like this. I did state that, when you do the math, a lot of it does miss. But when we look down in the pool deck area, remember my roach antennas, I call them, the antennas that stick up? There are 2 of them at least. 2 at least. Now, I don't see it going the other direction. I see it going one direction to 2. So this is interesting, the crossed direction would want to count also, wouldn't you? But I show that in the content where the column is like that, and you got the rebar up on it. All right, so for that rebar to have, to not just simply punch down. All right, so let me pause. Where you go? Great. Sorry about that. Give me a second to figure this out. Oh, there it is. So, for example, when you see the scratch marks, remember I did a video on the scratch marks, etc. That indicates rebar was right in line there to scratch across there. That it wasn't outside of it. It was there. Now that indicates like one piece there, but more there. We have these bent over. Remember I refer to them as rabbit ears. Your shear heads. They tell the direction also. I've got a better video than this to show, a better image. But while we're here, do you recall the imagery from the Herald that they shared showing the cracks? There's that column I talked about, and there's that rotation, that dip. And there it is there again. So your columns here, it was up here at one time. I know this is hard for you to visualize. I'm going to get into the garage, back to the built main structure again, but I'm letting you relax and look at it. As you can see, I got up, that one video got up to 1,400 views, and then YouTube caught on that it was my content on this, and they stopped it. It's like, it's gaslighting, and it's terrible to watch it go 1404, and then days later 1406. They're just torturing me. What they did, I'm sure people are watching it. But they're only going to let this number show. All right. I think that the count part of their shadow banning trick is probably able to change your count, because I saw the count. I showed you another video. The count was way up there. One of my videos was at 13. You guys saw 500, and that was hours apart. And I saw in the algorithm it said 1,300 views, and over here it said like 500 some change. And then next thing you know, this sort of tapped off, and I think it made it to 1,500 around then, and then this matched up to it, and it just went no further. So I think that's another form of their shadow banning, their gaslighting, their nastiness. I put my stuff international too, and it's in the millions of views there. All right, and I get $0 for that international thing. It's not monetized, $0. So you're seeing millions of views. That's $0 towards me, just so you know. About 1 million views, people make on YouTube make $5,000 per million views. You do the math, divide up whatever they're doing, and now you see why some of these people just come out of the woodwork just to do content and just to put out anything just gibberish. Let me go on. Well, I do a lot of jabbing, but here we go. So here's a a piece of rebar that I'm referencing. Circle it there. Remember, let me just do the deck for you, and let's put the head here. All right, we'll turn up a little bit like that and there. I guess I should do a cleaner for you. I apologize. So here, let's do the deck like this, all right? And the deck's continuous, even though I'm putting a seam there. I'm taking liberty, and I'm going like that. I'm taking liberty showing you the deck goes right and left when it goes down, if per this image. Now there's the rebar. You can make this top rebar as long as you like, 40 foot long, I don't care. Except for we know that the length here is what you observe. So I don't care if you use a 40 foot long piece. This piece, this section here, is this section literally what you see left behind. That's your overlap beyond the head. That piece is literally over the center of the head. That's the piece that came down. So when this deck butterflies apart at this side, at this section, left and right, we see that this part of the reinforcement longer engagement, and this part is closer to the top. Also has the car cycle loading. Cycle load, and that creates a weak bond. Ultimately, when the car section area goes down, this bond over here is what's broken. This bond stays intact. I literally know that because it's on the floor here, how that bond stayed intact with the floor. This is the floor here, which is the pool deck side, other side of the planter box, and it was able to pull this section out of the existing side. And when I say pull it out, it failed. That side of the section failed. Had it not failed, we would still be looking at a flat deck, an existing deck. This is in my collection, and it's not my arrow. It's just something I downloaded, showing it initially how a lot of people, and it's fair, got the buildings confused. This is a kitchen here, and down here is just openness. This is the other building. This is the other building, not, this is north, not south. And this is probably where they're trying to say maybe Cassandra is, but 1, 2, 3, 4 is, I think, where you would get if she was over there, but then this is the first floor. So 2, 3, it would be this one. Charles and I, we've gone back and forth about that, right, Charles? As a putting her inside as opposed to putting her outside. I want to use this drawing here and talk about the load path again. So this, I believe, this is not there. This is an elevated deck like that, and then it's got then you're down here. It's 11 foot 10, I believe, right? And it's 13.6. So that's your 11, and it's about 7 foot out, and then about 7 more inches. And then you're in the inside, the 13.6 floor. 13.6 floor. As you go past the hallway, you go up again, though. There's another bump. And then you're in a utility room. Then you take one more bump, a significant bump, and now you're in the pump room with the sprinkler system, etc. That would be above this area here. This is roughly the let's see, hallway. So hallway. Maybe the hallway's there, and then this is roughly the washer dryer room, and then this is another bump up into a utility room right here. So just want you to understand that this doesn't exist. It's an elevated slab, 1 foot 6 inches, so somewhere about there. So the load path is kind of different. It comes across here. I think this might be existing to the 1 foot 6, but the car pathway, I think, goes up like that, and then you pick up your deck. Then a drop down. There's a planter, a garden box down there, a little lower garden box. But this is 11-inch elevation. 11-inch, I believe, elevation off the deck, off of the 11 foot 10. Am I right? 11 foot 10 is 11 foot 6. 13.6. Yeah, I get them mixed up. So, you move all this time, I still get this stuff mixed up. Let's call it 11. Let's 11-inch 10. Maybe 11, I'll find it, but you understand that this is an elevation change here. And looking at it from this view, out here is where they did a core sample, Here's the planter box. So right about there is where they did the core sample. That core sample shows as a shear fracture. If you understand my understanding of how I explain shear fractures, here is the rebar, and here's the concrete around it, right? But this is all fractured, and I'll show you. I'll go down this rabbit hole with you again, another video. As decks deflect, think of the beam as I told you about. I'm going to erase this and give you the beam draw over. So remember you're loading a beam here, just loading a beam. All right, point loading, and I'm showing this as deflection, if you will, of the beam, instead of drawing it in. Remember your bottom steel's here. As this deflects, everyone calls this a shear fracture. Before this shear fracture develops, number one shear fracture. This other crack is number 2. Change colors, but keep it like it is. I'm going to add green. So the fracture, where depending on where your load is, we'll do this. Come across first, and then the secondary fracture changing to yellow. Let's go with this color. It starts working its way up. Now this is just cover down here, so it's a pretty fast break. And then this one is what's left is a little bit of a workaround. So there's some little bit of grabbing here, some fracture happening, a little grabbing still happening. And then as it changes, as it loses its grip force, it becomes a little more sharp back towards the load point. And you still have top reinforcement that acts as a strong back capacity. So it's not for free that this is up here and you get to ignore it. No, it has a profile to the concrete still. And that profile, based on that loading, will identify itself clearly as this section. Okay. And the other section to the left. Well, I just got rid of that, didn't I? So it would be that section, and then it would be this section. And your loading is however your loading is, wherever the loading was. And I'm doing that for just to help you with deflection. That's not a number, that's loading. Okay? So the deck's deflection out here, let's erase that. These decks, let's just do a large span. They're integral, besides their construction joint right about there. It's integral up to this part here where it has that 11-inch rise. Where it has the 11-inch rise, and then down 1'6", and then it's like that. So that's over here. And then back over here, 1'6" elevation, and then we're into the 13.6 in here. I think it's 13.6, not 11'10". 13.10? Nah, I like 13.6. So that'd be 11.6. 1'6". Let me get this over. 1'6", 11'10". 13.6 inside. 13.4. Is it 13.4 inside? All right, you guys correct that if you would like. Okay. So here's our pad going over to the wall. The deflection is this. All these offsets are an issue, but the deflection is happening between here and here. And that gets us that tooth thing I talk about with the concrete. All smeared, all fractured apart. Same thing so the deflection of the deck, the span over time, hidden by the tile work, hidden by the tile work actually being a load on it. I didn't see the rebar that they cut actually as being swollen. It looked like it's pretty dimensionally stable. So to me, this is more like a deflection thing and not a water swelling fracturing deal. Because the rebar doesn't look like it's swelling and fracturing. It literally swells up and fractures. It didn't look that way, so I go to deflection. Let me move on. So I guess for clarity on this is their drawing. It should be, the deck should be across here like that. And that's your 10'6"? Is that it? 10'6"? Yeah, 10'6". There it is. Your 10'6" is like that. And right about here is a core sample coming in towards us. So if I come this direction, core sample right by the planter box. And so outside the planter box, internal a little bit. So it's up here like this, and then this is 11-inch rise up to here. So this isn't down here. This would be up here. Okay, so, and then there, so that would be up there like that. So this one doesn't exist, even though it's in this newspaper's rendering. So it looks like that. And this is where our rebar out here looks like that bad tooth rebar, their sample that they show when it's all fractured. Rebar, I think we got another fracture in here, and that's the laid down sample of it. So here is another additional 7 feet. So that deflection is, our span. This is where they got the drop slab detail here, the 11 inch. I think we get 11 inches here is where it steps up. So it's got another little drop slab detail going on there also. And this is the top deck, but it's not even with the house going into room 11. It still has it. I think this is 7 inches per original plan. So you come out, you take a nice safe step of 7 inches. You're on your upper deck, which is here. Upper deck. Yeah, I just spelled that all funny. Upper deck, I put a U-P-E-P-R. That's my brain for me. U-P-E-P-R. Woo, all right. Shout out to myself. So your upper deck. Did I get all the words, the letters right? U-P-P-E. Yeah, I did. I just inverted it there. Yeah, I do that typing too. So I have that crazy ability to screw that up. Here's the, this is the first deck they step on. Then this is that 11 inch. Then we're down here, and then there's another little deck like that. So now we're down here, the 11 inch deal. So the there's that grassy knoll. I couldn't resist grassy knolls here. So if you see the samples fractured way out here, what's over here? Just the anchor point. Let's clean some of that up. Let me clean it up a little bit. I'm gonna go backwards a little bit on it, but I don't want to get rid of everything. I don't want to start over. So we have our anchors. The anchors are showing as 90s, not hooks there. So that's important to know that also. So let's just change colors for you. Do this. So we have a rebar here, but now let me take some liberty and just move it, do this, and I'll hook it into this. All right. But at this location, profiles as this sample here. So the deflection, and it's close to a column, so it's close to a critical shear zone, with the reinforcement should be going across there. It's close to that, and yet it's showing as failing there with that core sample. Now that's also failing over there by the planer box, right by these guys. So it shows that our critical shear zones, of course, this is my opinion, and I dare somebody try to disprove it. All the critical shear zones are nothing. None of them count for anything because there's no, I call these a little internal capital. Yes, capitals go below and all that, right? But what's left behind is the capital, as what I like you to think of it as. So you can Google it and you look up capital and you might get an idea. But the critical shear zones, none of these are left behind anywhere on the structure. None are left behind. So it just shows you that the columns just had punching shear, but failure also of any critical shear zones, any of that extra reinforcement they added there. That and the core sample shows that because it's so close to the column there. That core sample should be inside that one critical shear zone, which they drilled through, eliminated it, and they were supposed to structurally put it back. They did not. Well, let's move on. So as I revisit the sample for you, this little piece there, that's the chair that they use to hold the reinforcement. So it seems like there'd be some more reinforcement. I'm sorry, let me dip it like that. It seems like there'd be some more reinforcement there. And there's that another section of reinforcement. I don't see the other reinforcement there. Weird, but there's a chair. There's that tooth, like a tooth grinding thing going on. See how it's missing? Now, if you can move the tape measure, you would see more grinding. So there was some deflection and elastic behavior going on with this deck. It was deflecting, loading, coming back, deflecting, loading, coming back. And this was a core sample. It was all fractured like this. As you remember, that one engineer tried to challenge me on that, saying, those samples happen like that all the time. And I was like, yeah, well, that's not a good sample. And he got upset. He disappeared. Now, I said I would get us back into the building. I'll give you a piece of it. And I said I would talk about this wall here. If you notice this wall, even counting the excavators, right? The excavators going at this structure, bending, deflecting, tearing up shit. Look at the wall itself. You can see there's no, I'm going to remove this, but there are clean edges. So that tells you during this collapse, it didn't go back and jam against that wall. So the direction was away from that wall. Let me clean it up, as you can look at it now. We know that through the video, but nevertheless, I'm still wanted to get you talk about details and you know, putting us there. This has debris underneath of it, so there was some material that got shoved underneath before it came to rest. So that's an interesting tell there. But this wall, and it has more to tell, this wall, it's the longest length of it, but I wanted to show you that this indicates that there was no, the driving, when it started going down, it did not go in line with that. So is that video, the one I told you with the 2.5 hour videos, I spent time looking at it. You can see the reinforcement here. Again, if this was on the outside of this, well, you wouldn't see it. It would just go right down, but you can trace it right down to there. You can see the scratch marks of the reinforcement also there. So to say it didn't have reinforcement across the heads is just, it's misinformation, all right? The engineers are not catching on that you're looking at the reinforcement right there. And to look at it there means it was not side by side, or you would see it like this, no reinforcement exposed. But to see this reinforcement exposed here and here is indicator that it was across the head. So let's just put that to rest, that it did have steel. Now, I'm not saying it had steel in both directions, but we see that there's a little nub there. I did this before for you guys. I zoomed in and showed you your other reinforcement. But the problem is, it could be some wire or something that's right there. That's from the overlay. But this has the reinforcement here, and you can see the engagement of the paste. Here it seems like less engagement of paste. This seems like more engagement of paste. So there, it seems like it lost, engagement over time. This does look like part of the structural deck, not the slab. The slab, I don't recall any steel being in it. And for that to be exposed, this is what I'm talking about. The head, it would have come across the head. Here's the concrete. I'm just going to take some liberty here. And it would have came across the head like that. Lost engagement on this side. And that's where engagement stayed. So this is engagement staying, and I'm going to anchor it in the drawing like this. This side is the deflecting side, initial releasing side. As it's releasing, the deck is going down. Deck is going down. Oh, wait a minute. There's their planter box. That indicates that the deck was going down on that side. This side's still gripping. As you can see, these aren't 10-foot pieces of rebar. They're 20 foot, 30 foot long. Might even be 40s, but now they're 20 foot long. You know how they couple it or not. But these are 20 foot long at least. And you're looking at, what, 8 foot? So the rest of this rebar is back here in the deck. This is the section to let go. And so anyone, the engineer stating that it didn't go across the heads. This is in this, because it seems like a few people coming out now. Engineer videos are coming out. This one is the webinar. There's another one I followed that it was maybe 6 guys on that webinar, engineers on there, and they're all saying that there was no steel across the heads. I'm like, there is steel across the heads. If it was along the side of it, we wouldn't see it up in the air like that. We would see it down on the ground. All right. So you can come here and watch this for 2.5 hours. It's maybe difficult for you to follow the language. It's English. But I followed that one, and I followed another, I don't know where it is now, But I have a bias. I want you guys to know I'm an anti-plate slab construction. Now, this is from India, so they call it flat slab, all right? USA, we call it plate. Same difference, so don't get confused. They're not saying it wrong. It's the same beast. All right. So I don't know, but you should listen to this if you want to learn. With only the guy is the one that I like. My bias is I hate plate slab. Rigidity. I think she goes into the ratios, depth ratios, which depth to distance ratios, which is nice. But the short answer is deflection is the killer. Without deflection, this deck wouldn't have gone down. So you can say, well, but it's because of the rust, the deck went, well, you got me to deflection again. If you can eliminate the deflection, you've got a stiff deck. All right, so initially, everybody likes a stiff deck. All right, so if you can eliminate deflection, that means you got no punching shear. And you can't have punching shear without deflection. Unless you get, you're going to get deflection. It's going to deflect at some point. You can theoretically try to tell me, well, the whole thing comes down. No, you're going to get deflection before that. There's going to be some form of deflection before that. And I'm stating again, without deflection, you get no punching shear. So deflection, stressing on the critical shear zones, which are very weak. They then punching shear develops. And it breaks through one column, and then the next and the next. The deflection was indicated to me per 1980 with that drawing. Remember the drawings where they do all the repairs, where that fracture is. They do some foam and some epoxying. I believe this goes here's the pool over here. I believe this is our butterfly area here. The whole zone. So that shows you your deflection is down like that. I've got a couple of videos in the can, as we say, backed up, for showing other structures with this deflection going on. But I've got tons of video. I don't want to overwhelm you guys. Just want to tell you, I keep up to date with this stuff. This is 4 months ago. This is their webinar. I found it today. And I think I'd like to end it with you guys coming over to this video here where I call critical punching shear, critical shear zones, and tributary zone, and deflection is mostly cause. Posted that 5 months ago. I just love this layout where he used stirrups in this zone here. And then there's a small span there. I so love this. And he went 4 directions with it. I so love this. This is going to create a stiff slab with very minimal deflection, depending on the loading, right? Depending on the concrete thickness, the cover still needs a finish job. But the stirrups and the extra overlapping of the stirrups done correctly, not just one ring around there. Oh, you see it took 1, 2, 3, 4 to get this just across there. That means he's like lap 3, then lap 3, and then lap 3. It's friggin' beautiful. Look at this video here. I love it. I would love to see how this behaves in real life, the completed project, how it went. I would like to see some more stirrups around here, though, lower down, closer. Well, I guess they're not done that yet. But this thing is exciting to me to watch that. It's beautiful. That's beautiful work. You can come to this video again. I don't know what I chat on about that, but that's the short version of it. It makes a two-way slab system that will behave in a two-way directional slab system based on the offsets. Make sure there's no offsets here. And when I say no offsets, no offsets. All right. If you're gonna do a slab, stop with the offsets. All right. Stop with the offsets. Make it all behave nicely, uniformly, loading across, especially with your rebar. You can't have these little short sections over here and expect to behave the same as this zone here with the short section here. That's just ridiculous. All right, I'm not into plate slab construction. I am anti-plate slab construction. All the evidence is showing that these buildings, 40 years, 50 years, are just just showing fractures after fractures, and they're dangerous. So if you live in a condo that's got plate slab construction, you should sell it. Yeah, I'm anti-plate slab construction.